Okay, so the first time that I actually held the this online um, review session, unfortunately, it did not save. So I'm going to upload this video, and it's basically just going to be walkthroughs of um, how to do things in preparation for the exam that you will have tomorrow. So what we did today is we basically just talked about what's on chapter 8 and chapter 9. And I'm going to start with chapter 8, and that is dealing with molarity, concentration, titration, dilution, etc. So a couple things that you have to be aware of is the problems when they're written and how to decipher where you will be putting things. So a couple of things that you need to remember, but that he will give you looks like this. Please note this is the same one, okay? Because we know that molarity equals the moles over liters, and all this is dealing with concentration. Okay, so let's go ahead and solve, let's do a titration example. So we'll start there. So for example, we want to determine the mass of acetic acid which by the way is this, that has a molecular weight contained in a solution if titrated 25.0 mils of the solution requires 43.5 milliliters of a 0.154 molar NaOH. Now, this is a really wordy problem. So the first thing that you want to do is go through it and decipher it. So we want to ultimately determine the mass of acetic acid. So over here, I'll put, and we know mass is usually in grams. So I'm going to say grams of CH3COOH. What is it? We're given the molecular weight of CH3, so that should be a huge indicator as to how you're going to set up this problem. We know that molecular weight is in grams per mole, and we can use this as a nice bridge for when we need to go from moles into grams. Okay, so we'll need this, and hint, hint, we'll also need to have a molar ratio, because again, the molar ratio gets us from when we're already in moles, which is moles over liters. When we're dealing with concentration, it's still the number of moles just per part per 1 liter. So in order for us to get to grams, we need a molar ratio, because we'll be in moles. We'll use the molar ratio, and then as soon as we have that ratio as to how many parts are in the whole, then we can go ahead and use the molecular formula to convert us into grams. So we will need to have a molar ratio. Now, this molar ratio should be given to you in the problem, which he does, so which he will do. So let's go ahead and write that here. We have NaOH plus CH3COOH will yield sodium ions plus CH3COO minus plus H2O. Okay, so there will be the equation that he'll give you, and I will 9 times out of 10 it should be already balanced for you, unless he tells you please balance. Okay, but most of the time it will be balanced, and as we can see here, each one of these have a coefficient of 1, 1, 1, 1, and 1. So really this is one ratio. So when we're dealing with a molar ratio, you need to take in effect the coefficients. Okay, that's what I mean of the molar ratio. Okay, so let's go ahead and continue the problem. So we're going to want to start with the volume. Always start with the volume. If titrated, if I'm titrating 25 mils of that solution, I have 25 mils, but I need to have this much of NaOH. I don't want to start of the total end of the amount of titration, okay? So this right here is not pertinent for the problem. If titrated, if titration of the solution. So we don't need to worry about this because that is of the solution titrated, but we do need to know how much of that solution will require of the sodium hydroxide, okay? So always start with what's needed, okay, what it's asking for. Don't pay attention to this. And a lot of students are like, well, why don't I just take this 25 mils? Well, you don't need to because that's of the acetic acid, okay? We need to have the 43.5 of the sodium hydroxide, okay? So what you'll first want to do is go ahead and convert. Let's see if I can make this screen a little bit bigger. We're going to go ahead and convert our milliliters. So convert milliliters to liters. And the reason we want to do that is because up here we know that molarity is moles over liter, not milliliters, okay? So that should be pretty simple for you. You'll have 43.5 milliliters of NaOH over 1,000 milliliters of NaOH for every 1 liter of NaOH. So now we've successfully gone from milliliters to liters, and we are left with 43.5 or 0.435 liters of NaOH. Okay, this could be easy. You don't even need to show the step if you know you can move the 3 zeros. Okay, so now that we've converted milliliters to liters, we're going to go ahead and start with the rest of the dimensional analysis. Okay, so up here we know that if we have this many liters of NaOH and we're given this already is concentration, remember this part right here is moles over liters, and we just converted the liters, right? Because he's given us the volume here, so moles over liters, right? But he put in milliliters. So we can just go ahead and put those things together. And we can say that we have the point, we'll have 43.5. Oh. Okay, so how do I do this? Well, we have the amount needed. Okay, we've converted it to liters. We're going to cancel out our liters. Okay, and you're thinking, well, why didn't you put this on the bottom, Liz? Well, you don't need to put this on the bottom because if we put mils on the bottom, right, that's going to give us a different value. So here we're going to keep it straight across, and then we can now use what I like to call the molar ratio. We'll go here. So what you're trying to find the mass of is the acetic acid. So what you need to find the mass of will always go on top. So if you're confused about what do I put on top, put what you're looking for on the top. So in this case, we look at our balanced equation and everything is 1 to 1. So for every 1 mole of CH3COOH, we need 1 mole of NaOH. Now here we go, our moles have canceled out, the liters have canceled out, and our milliliters have canceled out. And now we're going to go in and we know that moles, molecular weight. So up here I'll say molecular weight equals grams per mole. right? Grams being on the top. We know that there are 60.1 moles, grams, I'm sorry, per mole. That's the molecular weight, okay, of NaOH, of CH, I'm so sorry, of acetic acid, so CH3. And then down here, we can just put moles because we're now just talking about here. What this molar ratio does is it cuts out this NaOH so that we're just left with the CH3COOH. That's why I always use like piece of the pie examples, because if here's my entire pie, right? And that entire pie is equivalent to NaOH plus CH3COOH, acetic acid. I just want to know out of the pie the acetic acid component, which is just this much, okay? Let's just say, hypothetically speaking, this is how much the CH3COOH takes place in the mixture of it, right? We'll need more NaOH to dissolve the CH3 or less or vice versa. So I just want to know the CH3 component of this whole thing. So here we have canceled out our NaOHs. Now we're just dealing with CH3COOH, and you can go ahead and solve this whole dimensional analysis, and it will bring you to your final answer, which should be 0.403 grams of CH3COOH. Okay, so something like this could be on the exam, and this is dealing with titration. So if titrated, okay, you need to make sure you figure out and choose the right ones, okay? The titrating is what, when we titrate something, remember that's what's kind of pushing down and separating. What's the point of a titration experiment? We should know that. So let's go ahead and do another one with percent mass. So actually, let's work on, let's do this percent mass. So calculate the mass percent of a solution prepared by dissolving 17.2 grams of NaCl in 149 grams of water. Okay, so when you're dealing with the mass percent, remember again, the piece of the pie and the pie itself. Okay, in this case, this piece of pie that we're trying to calculate is what? The 17.2 grams of NaCl. We just want to know the NaCl, right? So just to divide out that NaCl, we'll do NaCl over NaCl plus water. Okay, so that's going to give you 17.2 grams over 17.2 grams plus 149 grams. And that's going to give you some number X. After we do that, you need to multiply that to put it in the percent form. So then you'll get the mass percent equals, it should be 10.3%. Okay. So basically all you're doing in solving mass percent is what is it that you are doing the dissolving in the solve. So if we think about terminology, it should be solute over solution. Times 100%. Okay? What is getting dissolved in the entire solution? So some of that could be on the exam. Now we're going to do molarity of a solution. Okay, so now we'll say what So what is the molarity of a solution formed by dissolving 45 grams of sodium hydroxide in water to give a final volume of 250 milliliters? Okay, so for something like this, how do we begin figuring it out? Well, we need to know molarity. Molarity equals moles over liters. So here we have 250 milliliters. So the first thing you want to do is convert that to milliliters. So in order to do that, we know there is 1,000 milliliters for 1 liter. So we should get 0.250 liters. Okay, so that is this. Okay, now the second part is we're given grams and we know we need to get moles, and the only way to go to moles is to use the molecular weight. So you should have the 45 grams of NaOH by the molecular weight of NaOH, and that will give you some number. I don't have my calculator, so I'm not doing it. So then if we get to this point, we have this be the number of moles. Okay, so now all we have to do is plug in the molarity equation, which is mole over liter. So we'll have whatever these number of moles were over, and that over the 2.25 liters, and that's going to give you the number of the big molarity, which should be 4.5. I guess I'll double check right now. If the molecular weight of NaOH is 39.997, then we'll have 45 divided by 39.997 equals 1.12. So 1.12 divided by 0.250 equals 4.5. Okay. Again, molecular weight can just be found by using the periodic table, looking these up and adding them together. Okay, so we know 16, 1, so you can go ahead and add those up. Okay. All right. Another good question that we want to do is this one. What volume of 8.25 molar NaOH solution must be diluted to prepare 2.40 liters of 0.500 m NaOH? This is a huge one that students forget. To prepare this, okay, to prepare. So right off the rip, you know you have concentration, you have a concentration, and you have a volume. So we should be thinking this already. C1V1 equals C2V2. Like I said, I don't really use that one. I just think of it in terms of M1V1 equals M2V2. Why? Because we're already given M as a unit, and for me, that's easy to just kind of for my brain to use. But remember that these are equivalent. So we know right now that we have 1M, which equals 8.25. Do we know our V1? Do we know our M2? And do we know our V2? Maybe. So let's look at our other M2. We're given a 0.500 M. Okay. Now, what volume of this molar solution must be diluted to prepare? So this right here, this 2.4 liters, is this going to be my V1 or my V2? It should be my V2. And why? Because we need to prepare that many. It's telling you to prepare, you are preparing 2.4 liters of this 0.5 molar NaOH. And the question says, what volume of this higher molar NaOH? So really, we don't know our V1. And students, right when they go through reading a problem like that, the first time that they see a volume, they automatically associate a 1 to it because we are used to and trained to do that. So the first sight of a volume, we're like, this is our V1. But the question itself is saying, what volume of this higher molar NaOH will be needed in order to dilute and prepare to be diluted to prepare an 2,4. It's telling you that I need this much of this. Okay, so our unknown in this case is the volume of our very high molar solution. So now we can just go ahead and plug and play. We'll do 8.25, right? Because that's the molar, that's M1. And we have our V1, we have equals M2 and V2. And so our V2, I'm just putting it as X. And our M2 is this 0.500 times 2.40 liters. We don't need to do any conversions, okay? We're in liters, we're in moles, moles per liter, molarity, concentration, all good, okay? This is a dilution problem, so make sure we did a titration already. Make sure you're aware of what it is to be diluted and how to set this up, okay? Follow the proper measurements. Pardon me, so we'll have 8.25x equals 0.5 times 2.4, and that's going to give me 1.2. Okay, units are arbitrary here. We're going to divide by 8.25. Which gives me 0.145. And then in this case, this is in liters, okay? So make sure you know that everything dealing with this is this. So this is in liters. I have seen him trick students and convert it to mils to make it look like a bigger number, okay? So if we saw this, we would just know that if we times this, not times it by, what am I thinking? If we times that by 1,000, then we should get 145. Oh no, oh, it does that all the time. Awesome. Okay. So I'm sorry, and this is still terrible. Great. Basically, the takeaway from this minus the slop is that if you got 0.145, that 0.145 is in liters. If you don't see that as an answer, you can go ahead and convert easily to milliliters and it will be 145 mils. So just be aware that maybe you are doing the math right, just that he's trying to trick you with conversions and he's putting things back into mils or something of the sort, okay? But know that they are equivalent. Awesome. Okay, and then let's go ahead and do say he gives you a problem and it says determine the final concentration of a solution prepared by diluting 25 mils of a 1.38 molar. So we know that that 25 mils belongs to 1.38 moles of HCl, okay? And that our final volume, we're asking for VF, okay? We don't know, or we don't know the final concentration. VF, we do know, we should know that to be the 0.5, right, liters. So VF, V final, is 0.500 liters, but we need to know, we need to figure out, is that, how would we figure out our first mass? So we know we're going to use M1V1 equals M2V2. We know that. And we want the final volume to be this, okay? So we need to start by first taking this 25 mils, okay, and converting that mils, we can take that and convert it to over liters. Or do we have to? That's the main thing, is do we have to convert this to liters? Okay. And it's like, yes and no, but what we can end up doing is, I would take this though and just say, I would take this and say, if I took this and put it into 1,000 milliliters to 1 liter, then we'll get 0.250 liters. And then we can say we have this moles, okay? We have our moles of HCl. So if we have our moles of HCl, what can we do? We could take the 1.3, oops, 1.38, 0.250. Oh, I forgot a 0 here. That's why I'm getting a weird number. Watch your math. It's very easy to mistake. Okay, so first things that I would do is I would take this and convert it to liters, so then we get our liters. And then you know that you're given this molarity, and that's basically, again, to reiterate, molarity is moles per liter in concentration. So really it's still just moles. This 1.38 is the number of moles, but we say per liter because it's dealing in a solution. So I would then just take this whole thing and I would do 1.38 over 0.0250 liters, and that's going to give you 1.38 divided by 0.025 is 55.2. Okay, and now we're kind of getting a little wonky here. So if you start doing it this way, you're going to start running amok of, well, I have this, but now how do I deal with this 0.5 liters? Okay. So what I would do is, now we have liters, so we can say this is still on the top, right? So we have our 0.25 liters, and we're going to multiply that by 1.38. okay, per liter times 1 over 0.500 liter. So 0.025 times 1.38, divide that by 0.5, and we should get okay. So why did I do it this way? Okay, and these are the hardest problems to kind of work through. So for me, for another way that you could see this, and I'll do this in red, is if we take this mils and leave it in mils, but take this liters and turn it to milliliters, okay? So if I were to do that, then it would still give me the same units, okay? We would have 25 mils times 1.38 moles per liter, okay? And then times 1 over 500 milliliters. Okay, it doesn't matter. It's still going to get us our same value. Okay, but basically this is just using this kind of equation. Okay, so something like that could be on the exam. More than likely it will be on the exam. Let's go ahead and do some chapter 9 now. I think there's between the last review that I posted on here and those few problems, you all should be pretty comfortable and confident in how to handle them. But I do want to review pKa, pH, and things like that for acids and bases, just because I feel like a lot of people are still pretty confused about that. So let's just go over a couple of things. We'll do pKa, Ka, and pH, okay? These two are related in a way because they are dissociation constants. Okay, for acids. And so what that means is how likely is a molecule going to completely dissociate, or will it only partially dissociate? And you can tell based on the pK and Ka. So if we have a low Ka, and these are inversely proportionate. So if I have a low Ka, I should have a high pKa. If I have a high Ka, I should have a low pKa, okay? And a low pKa is indicative of a strong acid. So a low pKa, a low pKa is a strong acid. High pKa, weak acid. Now, pKa-Ka deals with dissociation constants of our hydrogens, okay? That's why we don't really see strong base, weak base, because bases accept the protons. When we talked about protonation and deprotonation, please know that anytime you see H+, that is a proton, okay? Yes, it's a hydrogen molecule, but we call hydrogen molecules protons because all they are H pluses, okay? So when we have something like this, H2O, and we deprotonate, meaning minus H, meaning plus H, okay? When we deprotonate that, take away an H, we should have left OH minus, okay? And if we protonate, then we should have, that means adding an H, then we should have H3O plus. So you need to understand what deprotonation and protonation mean in terms of protons. All we need to do is follow H. That's what we do in acid-base chemistry. We follow H, okay? So dissociation constants just talk about the likeliness for full or partial dissociation of hydrogens. Okay. pH just determines if you're an acid or base, right? It's just like the conditions. It's on the scale of 1 to 14, okay? So it's scaled, and it just is kind of there to help us calculate if you are acidic or basic overall, okay? pKa is a dissociation constant, which lets you know specific molecules and their chance to separate, meaning hydrogens, like for example, let's use this, a new color. For example, this, we'll say, what is the likelihood of hydrochloric acid and water, right? What the chances of these to fully dissociate? And we know that hydrochloric acid definitely can do this. Okay, it definitely 100% dissociate because it's a strong acid, and we know strong acid just because we've been told that over and over. But we know that hydrochloric acid is a strong acid, so we can definitely have access to this proton here and do some work with it. Okay, so that's what we're talking about, are the chances for it to dissociate 100%. Okay, something that doesn't fully dissociate would be something that looks like something like this, okay? Even though we have this H in the front, this right here is very happy together, okay? So we're not gonna get, this might partially, we would call this a partial dissociation because yes, we can remove the H plus from it, but the rest of this molecule, this C2H3O2 thing, this is gonna stay together. Okay, it's kind of just like a hydrocarbon in a sense, even though we have oxygen present, it's going to just stay together. Okay, we're not going to expect that we can strip these hydrogens out from it or these oxygens. There's just no freaking way. Okay, it's just not going to happen. But we can still get some partial dissociation because we do have a free floating H that's the front of this molecule that we can easily strip from it. Okay. In fact, this would be. Okay, so anyway, that's what we have to deal with when we're talking about PK, KAs, etc., and what we should be familiar with, okay? Now, the next thing that we need to talk about is how do we determine PKAs and KAs, okay? So if you're given a PKA, or you need to solve for the PKA, but you were given the KA. The KA, hint, hint, will always be in some sort of scientific notation. So it will look like this. Remember, I told you that these are inversely related, okay? When we're solving for this stuff, we know we're going to use log, okay? Because this log of the acid is, this log concept comes from the Henderson-Hasselbalch equation, which I shall put for you down here as HH, Henderson-Hasselbalch, okay, equals the pH is equal to the pKa plus the log of A over HA. Okay, so this is the conjugate base, and this is the acid. Okay, so we know that pKs have dealing with logs, so we deal with logs here. So in order to find the pKa, if we're given the Ka, all we have to do is take the negative log of the Ka. and that will give us the pKa. Okay? I've never seen him ask you to solve for the Ka. Given the pKa, I haven't. But the reason we like to get into the pKa is because it usually gives us some nice value. And I'm going to say here a nicer value in terms of it may be, for example, it could be like 3.41. And this 3.41 is easier to work with than this 10 to the negative 4. Okay, so again, to get from the given the Ka to get the pKa, you will just take the negative log of the Ka, and that equals the pKa. Okay, and that's how you solve for that. Now, if we need to figure out concentrations of things and sort this way, let's see. So let's just go back. If we're talking about this, if you get a question that says, if you're asking for the hydronium ion concentration of a solution that has H plus is equal to this here, you guys, is the hydronium concentration. So in general, this is a trick question, and I have seen him use it before. If you're already given this, which is what we're solving for in the first place, because if you think about the Henderson-Hasselbalch equation, we're trying to find the amount of hydrogens, right? Which is why we do the conjugate base over the acid, because then it'll just help us figure out, because if we have, remember, if we're looking at something that looks like this, what cancels out here, right? And we're left with this, okay? So 1 over this, okay? So basically, we're just trying to figure out the hydronium concentration when we do the Henderson-Hasselbalch. So in this question, it's tricky. It's a trick question because he already gave it to you. So if we gave you the hydronium concentration is equal to 2.5 times 10 to the negative 4th, we know that H3O plus equals H plus, which equals 2.5 times 10 to the negative 4th. So if he already gives you that, that is the answer. There's no solving here, okay? And you might see something like that, and I just want to prepare you. Determine the hydronium concentration of a solution that already has this many hydroniums. Well, you figured it out. There's no solving here, okay? So let's go ahead and go back to like the pH questions and how to solve for those, because I think that a lot of students will have do some mix-ups there. So if you need to determine and the question asks for the proton concentration, okay? And it gives you the pH. Now, if it gives you the pH and it's asking for the proton concentration, pH equals the base 10. Actually, let's undo that. Proton concentration. So In order to find proton concentration, so H plus, but don't get this confused as in hydronium, okay? Like the last problem, they're all denoted the same. This is still just telling you the amount of protons, okay? Please read the questions carefully. For us to figure this given the pH, remind you, this is also not in scientific notation, okay? So for us to figure this out, we need to know that 10 to the negative pH is equal to the proton concentration, which then would just be 10 to the negative 8.75, and the answer should be 1.78 times 10 to the negative 7. And that's the amount of protons. And we know protons are very, very small, so this makes sense. Okay, so to determine the proton concentration given pH, we have to take 10 to the negative pH. Okay, this is it. 10 to the negative pH equals H plus concentration. This is something that you should know. Remember, pKa, to fall for pKa, given the Ka, it's negative log of Ka. Will give you the pKa. Okay, are we good? So if you're given this, take the negative log of that and you'll get the pKa. Two things to remember here. Okay, let's talk about Le Chatelier's principle. This is something that we actually quizzed relatively hard on, tested on the last test. So you need to state Le Chatelier's principle, or it would give into a multiple choice, and this is the end quote the definition that he gave me. A reaction at equilibrium that responds to stress, so to relieve the stress. What does that mean? X plus Y, Z, W. Okay? If we have products here, or I'm sorry, reactants there, what the heck? It's been a day. If I change anything by either adding more here, what's going to happen? You'll make more of this. If I remove some of this, what's going to happen? This will stay, right? So the reaction, if I add more reactants, will go to the right. If I lessen the reactants, we should see, because this is like this, we should see our products going to the left to make more reactants, because in acid-base chemistry, we can get this kind of left side, right side switching based on what the products and the reactants are. Same thing with here. If we add more products and we saturate this side, adding more products would shift the equation. If we're heavy here, we would be solving and fixing the reactants, right? We need to add more to the reactants. This would shift. And vice versa when we talk about removing products, okay? How can we maintain equilibrium? Factors that you need to pay attention to are temperature and pressure. Those are physiological things that are outside, right? So they're not just based on the molecules, the quantity of the molecules, or the concentration of the molecules, but now we're adding outside effects. So like if I had a gaseous state and I decrease the temperature, right, for those molecules that once were in a very high temperature area moving around quite frequently, if I lowered that temperature, then their movement would decrease, right? Which means that they would have more of a chance to kind of have an opportunity to have a reaction, okay? Even though they're colliding more kinetically, they're just bouncing and then ricocheting off each other, not having a moment to actually physically work. These are important things to think about when we're talking about states. So gases to solids to liquids, it's very important that you watch out for these factors of pressure and temperature and how that would push a reaction left or right to favor Le Chatelier's principle, which is how the reaction already at equilibrium will respond to something else. So added temperature, increased temperature, decreased temperature, increased pressure, increased or decreased pressure, adding more products or reactants, moving products or reactants, and vice versa for products. You just need to think about where this would go, okay? And think of them individually. Adding more of this, we would need to have more of this to maintain equilibria. Adding more of this means that it's going to make more of this because we have to think about equilibria, okay? Scale, it's a scale like this, and these are the scale plates, okay? Adding more here, the scale will drop down. Taking away, the scale drops up. Think of it in terms of a giant scale. And that is Le Chatelier's principle. Please know that definition. Another thing that we talked about were just verifying conjugates. Say you were given this molecule and you were told what is the conjugate acid and what is the conjugate base. Please remember that adding, if we take hydrogen and we're adding it, that is protonation, and that equals acid creation. And if we're taking the hydrogen and we're removing it, that is deprotonation, and that means base. Okay, so in this case, if we're asking what are these things, if I'm going to become an acid, then I need to protonate. So in this thing, I would have to add H. So adding an H to OH would give me H2O. And then its conjugate would be deprotonating to make it more basic. And that means that I'd have to subtract away an H and watch for charge. So then I would have O minus 2. Okay? You could do it for any example. Please note though that anytime you see OHs, we are dealing with strong bases. And one of his favorites is NaOH. You could see it as KOH, LiOH. Okay, anything that has this is very, very crucial to knowing that you're dealing with strong bases. Okay. Another thing that we went over was I'm sorry. I want you to know bicarbonate. Okay, when you see bicarbonate, please note that you're always going to have this. Okay, and this goes vice versa. If we have H2O and CO2 in solution, we're going to make bicarb. And the reason I want you to know this is because this is a very big biological factor in our bodies, and we create a lot of bicarb because we expel CO2, but not all of the CO2 because we can't actually get our lungs to remove all the CO2. So as a result, we're 70% water, so as a result, we will have bicarb, okay, which allows us to do a lot of things with this H, which is why it's fundamentally important to know this. But something that you could be asked is, which of the following compounds will form CO2 and H2O when it reacts with an acid? So if I have CO2 and H2O plus some acid, what it's asking is, which of the following will form this? Okay, so how do I make these plus some acid? So he'll give you a list of things and he could say, let's get back to black. He could say, CH3, NaC2, H3O2, MgOH2, or CaCO3. First of all, there's the science way to do it, the chemistry way to do it, and the not so chemistry way to do it. First of all, we're looking at these as our products, right? These are our products. Out of here, I know I have to have a carbon source. No, I don't have a carbon source here, and I don't have a carbon source here, but I do have a carbon source here and a carbon source here. But remember just a little bit ago, what did I tell you about something that looks like this if we were to triage this? This is more likely going to stay together. You're not having a hard time trying to pull that off. So just based on that knowledge alone, even though it has a carbon source, we know that that's kind of similar to a hydrocarbon and it's not going to be easily stripped. So the only option is here. Now, Liz, you ask, yes, Liz, why is that? We use calcium, sodium, potassium as something we call, what I call as charge satiation. And what I mean by that is these all have pluses, but CO3 is a minus. So how, without protonating it to make it this, right, how can we temporarily have this be carried? Well, we can just toss one of these guys on this CO3 and it will help balance out the charge. So now we can use that in a reaction when we create that with acid, a strong acid. So then what's going to happen is we'll make this is minus, this is plus, this is plus, this is minus. So then what's going to happen is this is going to pick up this, and this minus, and this will come together. And I'm sure you've all heard of calcium chloride, and now we've created bicarb. And so then from here, we can say, we can actually make byproducts from that because we'll be able to split that up with the extraneous amounts that we have in solution, because you don't just have one molecule. Remember, you have tons of bicarb, tons of this, tons of that in solution. So that's how we can form water and carbon dioxide. Okay? Okay, let's see. You could have a question that says, which one of these is not a strong base? So which one of these is not a strong base? Okay. Well, first of all, we know that it can't be this one. And it can't be this one because we don't see an OH. But if I added this one into the mix and I gave us 5 options, we know that this is a very strong base because we use it for everything. So that can't be right, right? We know this is a strong base. We know that these are the only 2 options that look a little sketchy to us, okay? Now, what's the difference between here and here? Even though we have 2 OHs and 3 OHs, look at what it's bound to. We have a metal and a non-metal. Anytime you see this metal with OH, please note that this, to be a strong base, okay, ionize, I guess that's how I spell it, it is now. Is in order to do strong base, you have to fully dissociate, ionize, meaning you have to get an ion, okay? This is not going to do anything because we can't strip this aluminum, this metal, from the bond that it creates with these OHs. Also, if you think about it structurally, right, we have all this steric hindrance here. the likelihood of trying to get rid of that with something that is so tightly bound to it is impossible. So what's going to happen is only you'll have partial dissociation with one of these OHs maybe stopping off, but not all three are going to fully dissociate. Okay, so the fact that it's a metal is a dead giveaway, and you should know that that won't fully dissociate. Okay, that's not saying that this calcium won't fully dissociate, but which is not a strong base, is definitely not this one. Okay, so aluminum. And I told you about the calcium. What do we use for calcium? He is just serving the spot as a ion or a charge satiation. Okay. Okay. Okay, so an isoelectric point is where the pH at which an amino acid has left that zwitterionic state. So when we're dealing with amino acids, and I believe it's chapter 10, as somebody told me from the last class, I just want to stress that a zwitterion, remember, you have a minus and you have a plus. Okay, and so you'll have two charges, opposite charges, that make this whole molecule, though, is still neutral, right? So there's no concern here. We didn't define any laws, but a zwitterion has points at which both ends or some ends could have an interaction. And so why this is important in amino acids is because technically we have a neutral molecule here, but what if I had a more basic amino acid touch on here and then nothing happened here? We had just had a more basic amino acid. Even though we're at like pH of 7 is neutral, if I add and go more basic, now I'm shooting at like 10, 13, 14, right? We're going towards more basic. But if I interact over here and I add more of an acidic amino acid, right? Now I can shift my pH to 1, 2, 3. Do you see where I'm getting at here? So all we're doing is, because of these 2 points on the zwitterion, because there's a potential 2 potential areas for an amino acid to attach, that amino acid's background, whether it's basic, acidic, neutral, whatever, can then, based on its attachment, can change the overall pH of the peptide amino acid. So that's all you need to know, is that the isoelectric point deals with the pH, and that pH changes when the zwitterionic state is left. Okay, and that makes sense because we're neutral here, but if I add basic amino acids, then I'm overall a basic amino acid. I'm no longer neutral, I'm basic. So maybe a pH of 10. If I'm in the zwitterion state and I add an acidic amino acid, now I've moved to an acidic pH, not neutral. Okay? Neutral, pH of 7, acid or basic, just think about not 7. 10 and 3, usually I do. Okay? Last one. First thing you need to realize what we're talking about is we're trying to prepare a buffer. What do buffers do? Slow the movement, or I should say slow and stop. I'll do it like that. Okay, they slow or stop the movement of hydrogen atoms. Okay, atoms. So if we have a reaction and we don't want to make the product, right? Because what's going to happen in acid-base chemistry is if you have a high source of proton on your left in your reactants, it's going to just go, fully dissociate in water, go until there's no more proton to be used. Okay, but say I want to not do that and I want to create some sort of buffer. In this case, we're using HNO2. What can I use to prepare a buffer? Well, I'll tell you right now, this. Like dissolves like. This whole thing is also applicable to acids and bases, especially buffers. Please stick with like. In this solution, we have this as the acid, and in order to make the buffer, we need something that's similar to the acid. Okay, so I don't need to add more HCl. Why? Because this is a strong acid, and on top of that, it's a really good source of proton. So if I'm adding more proton to something that's acidic, am I going more acidic or more basic? Right? I'm going more acidic, so I'm giving this reaction more of a chance to move to the right. I told you here is another proton source, and then we have this carbon chain that we're not going to do much with anyway. I identify that, know that, but even then I still have single H's, so I'm adding protons, and that's not going to buff it out or stop the reaction. That's going to encourage it to keep going because I'm having a proton source. Now we have sodium, we have this NaNO2 or NaCl. Where in my problem do I even have any Cl or sodium? These might be a plus and a minus, but what is this going to do to our problem? It's going to do nothing. So we need to go with this one. First of all, there's NO2. It's in our problem. Second of all, I told you sodium, calcium, K, magnesium. These are all excellent proton satiators. This is a base. Let's add more base, right? Because again, if we're thinking about acid bases, if I deprotonate that, I should have a conjugate acid, right? So if this is the acid, I should have a conjugate base. So its conjugate base would be NO2, and the conjugate acid would be H2NO2. Okay, so protonated, more acidic, deprotonate, basic. So this is the basic version. So here I have more base. Let's add more base, and that's going to slow the movement of those protons. So buffers, you need to think of it in terms of base, adding more base to slow down. If you add more proton, add more acid, we're going to keep trying to create that equilibrium will never be reached, and we're still going to keep trying to have this reaction go. Okay, so don't add a proton source. Okay. In a nutshell, that's basically what we covered in the review session. Please, if you have any other questions, comments, or concerns about the exam, that you go ahead and reach out to me. The problems that I did here have been strictly taken from past exams, so I find them very helpful. Please also review the last YouTube video. It's about 2.5 hours, maybe a little bit longer. I don't know, but it is worth it because some students have some really good questions. Today's review session was pretty good. There were a few questions. I highly encourage you to work through titration, dilution problems, understand terminology, right? Dissociation factors, pKa, Ka, what those values mean. The first thing to go on an exam is that students forget the terminology. So be confident in it. If I have a high Ka, what does that mean about my pKa? What does that mean in terms of acid and base? What does that mean in terms of of strong weak base, or I mean a strong weak acid, right? Because pKs are all weaks, mostly dealing with weak acids, but which one is the strongest of them? Okay, so it's just trying to understand and kind of conceptualize these big key concepts that make up acid-base chemistry. Please also note that when you're doing math, we have lots of water in solution, okay? It's not just one molecule of water, so just know that when he asks a question like, um, it's not just, okay, we have one little tiny molecule of water. It's in solution. There's a lot of them. So there's a lot of opportunities for hydrogen sources. Okay, and that's like a big key thing. Again, any questions, comments, please feel free to email me and I will walk you through them. Okay, good luck and you guys will do great.